Alright guys, so in this video we're going to be going over problem set 2. So let's start with question number 1. For each of the molecules below, categorize them as one of the following: aromatic, anti-aromatic, or non-aromatic. So just a little refresher, for something to be aromatic, it must fulfill a couple of criteria. The first one being it must be a planar, cyclic, ring structure. Second, it must have conjugated electrons. And third of all, it must satisfy Huckel's number, meaning there's only an odd pair of electrons. And going along with this planar and cyclic rings and odd pair of electrons, we only want, sp2 hybridized carbons and or atoms. So let's go ahead with knowing this in mind. Let's go ahead with the first one. We have this ring structure here. So let's go through our checklist. Is it planar and cyclic? Yes. Are the electrons conjugated? Yes. Are there an odd pair of electrons? I see 3, 1, 2, 3. So I would say yes. But is this sp2 hybridized all the way around? The answer is no, because this carbon right here has 2 hydrogens coming off of it, making this sp3 hybridized. So this is going to be not aromatic, or non-aromatic. Now let's look at the second one here. So let's look at, is it cyclic? Yes. Is it planar? Yes. Isn't it a ring? Yes. Are there conjugated electrons pairs? Yes. An odd number pair of electrons, I see 3, and everything is sp2 hybridized. So for these nitrogen groups, it's important to keep in mind that the electrons are actually over here. We draw them in, and whenever we don't see them drawn in, but these are not within the plane of the aromaticity p orbitals, so they wouldn't be contributing, but the 3 electron pairs in the center are contributing, which makes this aromatic. Now let's look at this one. We have a fused ring. Let's see, is everything planar and cyclic ring? Yes. Is everything conjugated? I would say so, yeah. Odd number of pair of electrons, I see 1, 2, 3, 4, 5, 6. So automatically we can kind of know, hey, we have something going on here. And sp2 hybridized, we see another one of these sp3 hybridized carbons here. So this is going to be not aromatic. And a little shorthand, if you guys are having difficulties visualizing what is sp2 and sp3, a good rule of thumb is any of the carbons that a double bond is touching is going to be sp2 hybridized. So for example, this carbon here, or this double bond is touching these 2 carbons. They're both sp2. Same with these guys. Same with these guys. Same with this guy here. It's just that this one right here, none of the double bonds are touching it. Like if we go to the first molecule, same thing here. These double bonds are touching these 4 carbons, making them sp2 hybridized, and this one has a lone pair here. It's just that this one down here with the 2 hydrogens is sp3 hybridized. Let's look at the fourth question here. Is it planar cyclic ring? We have to come back to that. Let's look at the other ones. First, is it a conjugated pair of electrons? Yeah, I would say everything is conjugated. Are there an odd number pair? 1, 2, 3, 4, 5, 6, 7. Yes. Everything sp2? Everything is sp2. But the important thing to keep in mind here is if we count the number of carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 carbons, which means that in order for this molecule to assume a very stable state, it's going to pucker of some sort. So this is going to be not aromatic because the number of carbons is way too big and it's not going to be planar. Let's look at this molecule right here. Is it planar cyclic ring? Yes. Is it conjugated? For the sulfur, there are 2 lone pairs right here. And I would say that this pair of electrons here is conjugated. So I would say yes. Odd number pair of electrons, we have 1, 2, 3. Remember, this pair of electrons is not participating in the aromatic, resonance. And is everything sp2 hybridized? Yes. That contributes to the aromaticity. So this is aromatic. Let's look at this structure here. Is it planar? I would say so, yeah. Cyclic ring, yep. Conjugated pair of electrons. Remember to always draw in our electrons. 1, 2, 3, 4. I would say they're conjugated. Is there an odd number pair of electrons? No, we just counted. We have 1, 2, 3, 4. So Let's come back to that. Is everything sp2 hybridized? Everything is. So when you have something that is, or if you have something that would be aromatic, but the only exception that is breaking the rule is that there is an even number pair of electrons, this is a very special case, which is so unstable, it's going to be anti-aromatic. It is very, very unstable. So now let's look at the next molecule here. Planar cyclic ring, I would say so, yep. Conjugated electron pair, I would say they're all kind of conjugated. Nitrogen is drawing the electrons. They can all kind of participate in resonance. Odd number pair of electrons. Let's count. We have 1, 2, 3, 4, 5, 6, 7 odd pair of electrons. Absolutely. And sp2 hybridized. Everything is sp2 hybridized. And in this case, both of these lone pairs are not in the aromatic plane. So if a pair of electrons doesn't have to be in an aromatic plane for it to be aromatic, then it won't be. Because nature is very lazy and it wants to assume the most stable state. So in order to do so, it'll not have those electrons be in the aromatic ring. Now let's look at this molecule here. Is it planar cyclic ring? I would say so. Conjugated pair of electrons? Yeah, I would say it is pretty conjugated. Now let's say odd number pair of electrons. I only see 1, 2 pairs. That is an even pair. And is everything sp2 hybridized? If we look here, I would say everything is sp2 hybridized. So just like the previous example, everything looks to be aromatic, but the only exception is the fact that there is an even number of pair of electrons, making this very, very unstable, anti-aromatic. Alrighty, so 2 more left. Here, automatically, I can already tell you, not aromatic. Don't even overthink it. If it's not even a ring, don't even bother. So let's look at this last one here. Planar cyclic ring. So planar cyclic ring, I would say so, yeah. Conjugated electron pair. Well, there's only 1 pair of electrons, so it's kind of hard to tell. Odd number pair of electrons. 1 pair of electrons here. 1 is an odd number. We're good. sp2 hybridization. Double bond is touching these 2 carbons, but this carbon up here is kind of left alone. There's 2 hydrogens coming off of it. So this is going to be sp3 hybridized, which makes this not aromatic. Alright, let's go on to question number 2. For the molecule shown below, draw the frost circle and corresponding molecular energy orbitals and determine aromaticity or anti-aromaticity. So in order to draw a frost circle, the first thing we must do is draw out a circle. The next thing we must do is look at our molecule. So in this case, we have a cyclobutene of some sort, and in order to draw the frost circle in the proper formation, we must take one of the vertices and just draw our cyclobutane like that. It's going to be kind of on our edge. If we had for example, cyclohexane of some sort, or a benzene ring of some sort, we'd want this vertice, or any of the vertices, to be at the very bottom. Something like this. It's very important to have one of the vertices at the bottom of the circle. So now we have this. At each one of the vertices where it touches the circle, we can draw our little, orbital for the electrons to reside. And now let's count the number of electrons. 1, 2, 3. 3 pairs. 3 times 2 gives us a total of 6 electrons. So we must start filling these orbitals, going bottom up, following Aufbau's principle and Pauli exclusion principle. You guys all love Gen Chem, right? So let's go ahead and get started. We have 1, 2, 3, 4, 5, 6. So in this case, we have no unpaired electrons. No unpaired electrons, so this is going to be aromatic. Okay, if you guys have any difficulties, if you're giving a heterocycle or something that is extremely weird, like this weird cyclobutene, I would recommend drawing a frost circle if you have time, because this really tells you if something is aromatic or not aromatic. Now, let's look at the last page here, nomenclature. So, as we mentioned and stressed many, many times in class, it's really important to memorize all of the parent chains and know what takes priority. So let's look at this first structure here. We see a benzene ring with a carboxylic acid group coming off of it, as well as an aldehyde group coming off of it. And if we know memorized our charts, we know that the benzene, or the carboxylic acid, takes priority, making this a benzoic acid. benzoic acid. So that must mean that this is carbon number 1. And if we go by the number of orders that follows the lowest number, we would go to the left, making the aldehyde group fall on carbon number 2 of the benzene, but we must give it the proper prefix, which is going to be methanoyl. 2-methanoyl benzoic acid. We don't want to space between these guys except for between benzoic and acid. Now let's look at the second one. We have this group here, CHO. This can also be another way to write out benzaldehyde. I know it can be a little confusing because, what if it's like a weird, like a benzoic acid of some sort, but just know whenever you see CHO, it's going to be an aldehyde. We also have NH2, which is, if you guys remember, this is aniline. So if we know what takes priority, we know that the aldehyde is going to take priority. So we know we have a benzaldehyde of some sort. And if we look at the numbering, we have 1, 2, 3, 4 is where the amino group comes off of. So this is going to be 4-amino benzoic acid. Sorry, not benzoic acid, 4-amino benzaldehyde. My apologies. It's important, really, really important to know that when naming these guys, we don't want to use ortho, meta, and para. That is more of the common naming and kind of, as referring to one group in relation to another. But when naming something with proper nomenclature, it is really important that we use the numbering system, no ortho, meta, para. Okay, now let's look at this final molecule. Now I know what you guys might be thinking, that this NO2, we see this all the time. Is this a parent chain? And I'm going ahead to tell you that this is a very common trap. You do not want to see NO2 and immediately assume that to be the parent chain. There's nothing special about NO2, even though it might look like it. So sorry to burst your bubble if any of you guys fell for that trap. So the important thing to go by here, we all treat them as the same priority of side chains, so we must go by the order to see what gives us the lowest number. So automatically I would start with the NO2, and then we go to the right to the chlorine, and then bromine, which lands on carbon number 4, giving us a 1, 2, 4 pattern. If we started on the bromine or some sort, we would get a 1, 3, 4 pattern, which isn't really following the lowest priority, meaning that this proper nomenclature is the way to go. So we just kind of order everything based off the numbers and then put it in order based off of alphabeticals. So we're going to start off with 4-bromo, this B comes first. And then we got 3-chloro, A, B, C, D, E, F, G. Yeah, I sing it all the time. My bad. I don't know why I wrote 3-chloro. It could be 2-chloro. Trip myself up. And then it is important that we know that this is 1-nitrobenzene. Because in this case, the nitro does not take priority as a special parent chain, so we still need to designate what number carbon that comes off of. If you guys are ever confused of whether or not to put the number, I would just put it, because you can't be wrong if you're right. So, thank you for watching.